Welcome back, dear students, to the new lecture on engineering mechanics. Today's class we are going to discuss on how to derive the equation for moment of inertia of a circular section about its centroidal axis. So as you can see here, we will consider a circular section having radius r, and we will consider elemental area at a radial distance of r and making an angle small d theta such that the elemental width is dr. So I can consider this small strip as a rectangular strip having dr and thickness as r d theta such that the area is r d theta dr. We have done the same thing in case of a centroid, so you might be knowing that. So I will consider a small elemental area thickness dr at a distance r. Area of the elemental area dA is equal to r d theta into dr. The second moment of elemental area Ixx along the x-axis I can write as dIxx, which is equal to the distance, that is distance from the x-axis, that is y square into dA. That is the total second moment of inertia about the x-axis for the whole lamina or the whole elemental area. I can write it as integral Ixx, which is equal to integral y square dA. Here dA I can substitute as r d theta dr. So substituting that, we will get the limit. This has to travel from 0 to pi, as well as it has to travel a radial distance of 0 to r. So the double integral will come, and integrating it I will get the value, that is integral 0 to pi and integral 0 to r sine theta the whole square into r d theta and dr. Because y we can write in terms of y is equal to, we can write it as r sine theta, and x we can write it as r cos theta. So in terms of r, if theta if we are writing, we can write y is equal to r sine theta. This we have studied in the centroidal case. Integrating this and applying the limits, I will get Ixx is equal to pi r raised to 4 by 4. In terms of diameter, if I am writing, I will get it as pi d raised to 4 by 64. Since this section is symmetrical, I can write Ixx is equal to Iyy, and I will get it as pi d raised to 4 by 64, which is very important for your current semester as well as your higher semesters. You are supposed to somehow remember this thing throughout your BTech. Okay. Now we will come across certain moment of inertia for composite area. Before that, you are supposed to by heart certain values for certain regular figures moment of inertia values. That is the first one, the moment of inertia of a plane figure, that is rectangular figure about its centroidal x-axis, and this is centroidal y-axis, that is b dq by 12 and d bq by 12. This you can remember like this, that is, you are having, first if I am taking the x-axis, then the x-axis is going like this. This is my x-axis. So the x-axis is bisecting, or the lateral direction to the x-axis is what? That is the depth, and the parallel direction, that is b. So if you are calculating moment of inertia about the x-axis, then Ixx, we need to consider the lateral direction cube. Lateral direction cube is d cube, then the other one b d cube by 12. So suppose this is for y-axis. Y-axis is going like this. Then the lateral direction here is what? The lateral direction here is b, and the parallel direction here is the depth. So if I am writing Iyy, I can write the lateral direction cube, that is b cube, right? The other direction is d divided by 12. So you can keep this in mind while applying this moment of inertia for rectangular section. Now the moment of inertia for a circular section having diameter, I'll take this diameter as capital D. Then that is pi d raised to 4 by 64, as well as in the y direction also it is pi d raised to 4 by 64, since it is symmetrical. Then for a semicircular about its centroidal axis, the centroidal x-axis is somewhere here. That is, I can write it is 1.76 d raised to 4. and about the centroidal y-axis it is coinciding with the same thing, that is I can write that this is pi d raised to 4 by 64 by 2, that is into 1 by 2, that is I'll get it as pi d raised to 4 by 128, because this is half of a circle and it is passing through the same centroidal axis, so I can write this is half of that. Similarly, for a quarter of a circle, it is 0.44 d square, that is Ixx, and Iyy is pi d raised to 4 by 64 into 1 by 4, that is 1/4 of that. I'll get it as pi d raised to 4 by 256. So you have to remember these values for the calculation part. Now about this is for a triangular section. About the centroidal axis, I'll get this one as bh³ by 36. About the base, I am getting this as bh³ by 12, and about the upper point R, I'll get it as bh³ by 4. At least you have to by heart this value. The other one you can get it through the parallel axis theorem. Now we will see a question number 1. We'll see a question: calculate the moment of inertia of the shaded area with respect to the centroidal axis. So you are supposed to calculate the moment of inertia with respect to the centroidal axis. So the first step is to find the centroid of this figure. In order to find the centroid of this figure, you are supposed to fix the reference axis. This is my x-axis and this is my y-axis. So with respect to this, I am going to write my attributes. That is, you need to find the a1, x1, such things you need to find. So I will divide this into two figures, that is, this is a1 and this is a2. So here a1 I can write it as, that is 6 into 6, that is I can write this one as 6 into 6, that is 36 meters square. And x1 is the distance of this from your y-axis, that is x1 I can write it as, x1 is this distance, that is 3 meters, x1 is 3 meters, and y1 is the distance from here to here, the total is 6, so this distance is, I can write as this distance is 3 meters, y1 is 3 meters. Similarly a2 I can write it as, a2 is 1 by 2 into the area of the triangle, that is 1 by 2 into 3 into 3, I get it as 4.5 meters square, that is 4.5 meters square. Then x2 I can write it as, x2 is the distance from here to here, that is, this is up to here, there is 1 meter, that is 1 plus, then the centroid is at 2 by 3 of 3, that is I'll get it as 1 plus 2, that is 3 meters. Similarly y2 is, I can write as from this x-axis to this point, that is 2 plus, it is at distance of 1 by 3 of 3, that is I can take it as this also, I'll get it as 3 meters. So your a1, a2, x1, x2, y1, y2 you get in this form. You'll get in this form. Applying the basic equation for x bar, you'll get x bar is equal to 3 meter and y bar is also equal to 3 meter. Now need to calculate the moment of inertia about the centroidal xx and centroidal yy, about the centroidal xx and centroidal yy. So I request you to update this table with some more figures, that is you need to get the absolute value of y bar minus y1, y bar minus y2, then x bar minus x1 and x bar minus x2. If you follow this step, it will be very easy for you. So you can write this one as y bar minus y1 is 0, this one is also 0, x bar minus x1 is 0, this is also 0, 0 meters, 0 meters. You get it like this. So if you update it like this, to apply the parallel axis theorem, it will be very easy for you. So I have this Ixx for this about the centroidal axis as Ixx1, that is for the first rectangular figure, minus the triangular portion Ixx2. Ixx1 using the parallel axis using the parallel axis theorem, I can write it as Ixx1 is equal to Ig1x plus AH square. Here as you can see, the h value here is y minus, because I need to transfer, this was our axis, I need to transfer it from here to here. H here is 0, so I can write Ixx1 is equal to Ig1x. Similarly Ixx2 is equal to Ig2x, because the axis itself is a centroidal axis, so there is no need of transferring it, because the centroid of this rectangle is coinciding with the centroid of this whole section when there is a deduction of this triangle. Similarly, the centroid of this triangle is also coinciding with the centroid of the whole lamina once the triangle is removed. So there is no need of this a h bar square term. If there is a need of h bar square, then these two tables would have been very useful for you. So substituting that ig1xx, I will get it as bdq by 12, and ig2x, that is about the centroidal axis for a triangle section, bhq by 36. I'll get the value for ix as 105.75 meter raised to 4. Similarly, applying it for this iyy also, you will get the same thing. That is, here also the use of these terms is these terms will be 0. These terms will be 0, and there is no need of the transfer of these axes. So you'll get this as iyy as 105.75, which means I can say this ixx and iyy is same because the centroidal or this axis cuts in both the axes. It is found to be symmetrical. I hope you have understood this. Now we will move on to one concept based thing, that is Pappus-Guldinus theorem. There are two theorems. We will discuss the first one, that is theorem 1 of Pappus-Guldinus. You can see a bar like this having h height. Now there is a reference axis, and the centroid of this bar is at a distance of r from the axis considered. Now what I am going to do is, I will simply rotate this bar having height h around this axis in this direction, such that once it completes 360 degree, I am going to get a figure like this, right? Because this is going to move like this, it is moving like this, and once it completes 360 degree, I am going to get it like this. So this is what the Pappus theorem says. That is the surface area generated. That is the surface area, I can say it as what? 2 pi r. That is the total circumference into height. That is h. That is surface area is equal to 2 pi r into h. The surface area, that is 2 pi r into h, is the surface area of a cylinder. So the Pappus-Guldinus theorem says, the first theorem of Pappus-Guldinus states that the surface area S of a surface generated by revolution of a curve about an external axis is equal to the product of the length s of the generating curve and the distance d1 traveled by the curve's geometric centroid. So here it says the surface area S of a surface generated by revolution of a curve. Here the curve is what? Here the curve is a straight line having height h about an external axis. So this is the external axis. This one is the external axis. This is the product of length of the curve. That is length, I can say that is h. Here that is the attribute same is h of the curve, generated curve, and the distance d1 traveled by the curve. The distance d1 traveled by the curve is what? 2 pi r. That is the distance traveled by the curve's geometric centroid. That is the distance traveled by its centroid. So I can say, I can generalize this as surface area is capital S is equal to S, that is the length of the curve, into distance traveled, that is d1, and we have to see the distance traveled is the distance traveled by the geometric centroid. So this is for the some of the regular cases, that is the solid. I can say the first one is cone. In order to generate a cone, I need to incline a line segment about an axis, you can see here, and rotate it in either clockwise or anti-clockwise, so that you will get the surface area generated like this. Similarly, for a cylinder, we have seen the case and an example of Pappus-Guldinus theorem. And for a semicircle, I need to rotate for a sphere, I need to rotate a semicircle such that I will get the surface area generated by a semicircle. I hope you are clear with this. You just go through this and we will see the next theorem, that is theorem of Pappus-Guldinus 2. We are having a plane lamina like this, r by h, and there is a reference axis. Now I am going to rotate this area with respect to this axis. So the centroid of this area will be at a distance r by 2 from here. Now I am going to rotate it this form such that I will be getting a volume, and this volume I can write as volume is equal to the area, that is r into h, and into the distance traveled by its centroid. The distance traveled by its centroid is what? 2 pi into r by 2. That is the distance traveled by its centroid. So then I will get the volume as what? Pi r square h, which is nothing but the volume of a cylinder. So if I state the theorem, the second theorem of Pappus-Guldinus states that the volume V of a solid generated by a revolution of a lamina about an external axis is equal to the product of the area A of the lamina and the distance d2 travelled by the lamina's geometric centroid. You need to see that is the distance d2 travelled by the geometric centroid. So here I can generalize it like volume is equal to A, the area of this lamina considered, into the distance travelled by its centroid. That will give you the volume of any object which is being rotated about a reference axis. You can see the second theorem. In order to get a cone or the volume of a cone, I need to rotate a right angle triangle such that I will get the volume of this like this. Similarly, in order to get a cylinder, I need to rotate a rectangle figure lamina so that I will get the cylinder, and in order to get a sphere I need to rotate a semicircle so that we will get the volume of a sphere. So this completes the Pappus-Guldinus theorem.